Imagine a structure so vast it completely surrounds a star, not orbiting it, enclosing it. A shell, 1 astronomical unit in radius, 93 million miles from center to surface. The entire orbit of Earth captured within an artificial construction. The surface area would exceed 280 quadrillion square kilometers. That's 600 million times the surface area of Earth. Enough room for quadrillions of inhabitants, enough solar collectors to capture the total energy output of the sun. This isn't science fiction. This is the Dyson Sphere, a megastructure concept so audacious, so powerful, that its existence would mark the dividing line between planetary civilizations and cosmic empires. And we might be able to detect them. In October 2015, astronomers noticed something impossible about a star called KIC 8462852, better known as Tabby's star. Its brightness dropped by 22% over a matter of days. Then it recovered. Then it dimmed again, irregularly, unpredictably. No known astronomical phenomenon could explain it. No planet is large enough to block that much light. No dust cloud moves in those patterns. No stellar process behaves that way. One astronomer, Dr. Jason Wright from Penn State, proposed the unthinkable. Aliens should always be the last hypothesis you consider, but this looked like something you would expect an alien civilization to build. A Dyson Sphere under construction. Today, we journey through the science, the engineering, and the search for the most ambitious structures ever conceived, and explore what it would mean if we found one. What you're about to discover will transform your understanding of technology, civilization, and humanity's ultimate destiny among the stars. Prepare yourselves. We begin. In 1960, physicist Freeman Dyson published a 2-page paper in the journal Science titled Search for Artificial Stellar Sources of Infrared Radiation. The paper was deceptively simple. Dyson asked a profound question. If advanced civilizations exist, how could we detect them? Radio signals, the traditional approach of SETI, might work. But Dyson realized something deeper. Any sufficiently advanced civilization would face an energy crisis. As civilizations grow, building cities, powering industries, supporting larger populations, their energy demands increase exponentially. On Earth, global energy consumption doubles roughly every 40 years. If this trend continues, within a few thousand years, we'd need more energy than Earth's entire surface can capture from the sun. The only solution? Go directly to the source. Dyson calculated that an advanced civilization would eventually need to capture all of its star's energy output, not the tiny fraction that happens to fall on their planet, but everything, the full luminosity of their sun. And the most efficient way to do that would be to surround the star with solar collectors. He wrote, within a few thousand years of its entering the stage of industrial development, any intelligent species should be found occupying an artificial biosphere which completely surrounds its parent star. This structure, later dubbed a Dyson Sphere by others, would be one of the most detectable signs of advanced life in the universe. The sun produces 3.8 times 10 to the 26th watts of power. Every second, it converts 4 million tons of VAS into pure energy through nuclear fusion, a process so efficient it will continue for another 5 billion years. How much of that energy reaches Earth? Our planet intercepts approximately 174 petawatts, 174 million billion watts. That sounds like a lot. It is a lot. It's more than 10,000 times humanity's current total energy consumption. But here's the critical fact. Earth captures only 1/1000th of the sun's total output. The rest radiates uselessly into space, heating empty vacuum, accomplishing nothing. A Dyson sphere would change that equation entirely. By surrounding the sun with solar collectors, a civilization could capture all 3.8 times 10 to the 26th watts. Not 1/1000th, all of it. That much energy would enable technology that seems magical to us. Transmutation of elements on industrial scales, antimatter production, terraforming planets in decades rather than millennia, starship construction using mass drivers, computing power exceeding all human thought combined by factors of trillions, life extension, perhaps even immortality, powered by near infinite energy for medical technology. Dr. Stuart Armstrong from the Future of Humanity Institute calculated what this means in practical terms as a civilization with access to the full output of a sun-like star could sustain a population of 10 to the 24 individuals at first world living standards. That's a trillion people. The numbers are difficult to even conceptualize, but the physics is clear. Dyson spheres aren't just possible. For any civilization serious about long-term survival and growth, they're inevitable. But there's a problem with the classic image of a Dyson sphere, the solid shell completely enclosing a star. It's called the mechanical instability problem, and it's fatal. Imagine a rigid shell surrounding the sun at 1 AU, Earth's orbital distance. Gravity from the sun pulls equally on all parts of the shell, so there's no net force. The shell is in equilibrium. But it's an unstable equilibrium. If the shell shifts even slightly, say a few kilometers towards the sun on one side, that side experiences stronger gravity. The imbalance grows. The shell continues shifting, accelerating until it collides with the star. Dr. Larry Niven explored this problem in his science fiction and concluded that a solid Dyson shell requires active stabilization. You'd need thousands of massive thrusters constantly firing to keep it centered. The energy cost would be enormous, the engineering complexity nightmarish. And there's another problem: materials. A solid shell at 1 AU would require approximately 2.3 times 10 to the 27 kilograms of construction material. That's about 600 times the mass of all planets in our solar system combined. Even if you dismantled every planet, Mercury, Venus, Earth, Mars, the gas giants, everything, you'd still come short by a factor of several hundred. The solid Dyson shell, as usually imagined, is physically impossible with the matter available in a typical solar system. But Dyson knew this. His original paper didn't propose a solid shell. It proposed something more elegant and actually buildable. What Dyson actually described was a swarm, millions or billions of independent solar collectors orbiting the star at various distances and inclinations. Each collector would be in a stable orbit, held in place by orbital mechanics rather than material strength. No instability problems, no need for active stabilization, just standard Keplerian orbits, the same physics that keeps Earth orbiting the Sun. A Dyson swarm could be built gradually, one collector at a time, over thousands or millions of years. Start with a few large collectors, use the energy they provide to build more collectors, use those to build even more. Exponential growth. Dr. Stuart Armstrong modeled this process, starting with the industrial capacity of a late-stage Type 1 civilization, roughly 1,000 years more advanced than current humanity. A Dyson swarm could be completed in approximately 1,000 to 2,000 years. That's fast on cosmic timescales, instantaneous, really. And the material requirements are actually feasible. Mercury alone contains 3.3 times 10 to the 23 kilograms of mass, more than enough for billions of large solar collectors if you don't need them to be thick. A solar sail a few atoms thick can capture tremendous energy. The engineering becomes even more elegant when you consider self-replicating machines. Send von Neumann probes to Mercury. They mine raw materials, build more probes, which build solar collectors. The process accelerates exponentially. Within a few centuries, the sky around the star begins to darken. Not completely, the swarm isn't a solid shell, but statistically, any light trying to escape will probably hit a collector. From the outside, the star's visible light output drops dramatically, but energy doesn't disappear. It's absorbed by the collectors, converted to useful work, and re-radiated as waste heat. That waste heat, emitted as infrared radiation, becomes the signature we can detect. Freeman Dyson's insight. A Dyson sphere would be invisible in visible light, but glow brilliantly in the infrared. This makes them detectable across interstellar distances. If they exist, we should be able to find them. But the evidence forces us to confront an uncomfortable possibility. If Dyson spheres are detectable, inevitable for advanced civilizations, and offer such overwhelming advantages, why haven't we found any? Beginning in 2013, astronomers using data from NASA's Wide Field Infrared Survey Explorer, WISE, began searching for unusual infrared signatures. The logic was simple. Normal stars emit most of their light in visible wavelengths. If something is absorbing that visible light and re-emitting it as infrared, the star's infrared output should be much higher than expected. Dr. Jason Wright led a team that analyzed 100,000 galaxies, looking for galaxy-spanning Dyson spheres, civilizations so advanced they'd enclosed most stars in their galaxy. They found approximately 50 galaxies with unusual infrared excess, but further analysis suggested natural explanations: dust, star formation, active galactic nuclei. No definitive Dyson sphere candidates, but the methodology was sound. Then, in a 2015 follow-up study, Dr. Roger Griffith analyzed individual stars within the Milky Way. The search focused on F, G, and K type stars, stable, long-lived stars where civilizations would be most likely to develop. Out of 100,000 stars analyzed, 17 showed anomalous infrared signatures that couldn't be easily explained by dust or other natural phenomena. These weren't proof, but they were interesting enough to warrant further investigation. And then came Tabby's star. In 2015, astronomer Tabby, hence Tabby's star, published data from the Kepler Space Telescope showing something unprecedented. KIC 8462852, a star 1,470 light-years away in the constellation Cygnus, exhibited irregular dimming events unlike anything previously observed. Normal planets cause regular, predictable transits, a small dip in brightness, typically less than 1%, every time they orbit in front of their star. Tabby's star did something else entirely. Day 793 of observation, 15% brightness drop. Day 1520, 22% brightness drop. Multiple smaller irregular dips at unpredictable intervals. Each dimming event lasted days to weeks. No periodicity, no pattern. 22%. To block that much light, the object would need to be larger than Jupiter, but Jupiter-sized planets would create regular transits. This didn't. Dr. Jason Wright, analyzing the data, noted, "We'd never seen anything like this. The pattern was completely inconsistent with any known natural phenomenon." Explanations were proposed. Cometary fragments, maybe a broken comet surrounded by a massive dust cloud, but comets don't naturally break into pieces large enough to block 22% of a star's light, and the lack of infrared excess argued against significant dust. Planetary collision, perhaps two planets collided, creating debris, but the probability of observing this extremely rare event in the brief time Kepler monitored this particular star is vanishingly small. Stellar activity. Variable stars exist, but Tabby's star showed no other signs of the magnetic activity that causes stellar variability. And then, Wright made the suggestion that would make headlines. The pattern was consistent with a large artificial structure, something in orbit around the star, not fully enclosing it yet, but blocking significant light. The media seized on it. Alien megastructure around distant star became a global story. But science requires evidence, not speculation. Follow-up observations were critical. In 2018, further studies revealed that the dimming was wavelength dependent. Blue light was blocked more than red light. This signature is characteristic of dust, not solid objects. Most astronomers now believe Tabby star's behavior is caused by an unusually dense dust cloud or ring of cometary debris, not a Dyson sphere, probably. But the episode demonstrated something important. If partial Dyson swarms exist, they would create detectable anomalous patterns in stellar light curves. We have the tools to find them. We just need to look at more stars. In 2022, a new search began, Project Hephaestus, led by researchers at Uppsala University in Sweden. Unlike previous searches that relied on manual analysis or simple filters, Hephaestus used machine learning algorithms trained to recognize potential Dyson Sphere signatures in infrared data. The team analyzed data from multiple sources: Gaia mission, precise stellar positions and brightnesses, 2MAS survey, infrared observations, and WISE survey, deeper infrared. Their algorithm looked for specific signatures: excess infrared emission relative to visible light, lack of other infrared sources, no nebulae, no dust clouds, stable position, ruling out asteroids or comets, and located near a star of appropriate type and age. Out of 5 million stars analyzed, the algorithm flagged 7 candidates with all 4 criteria. 7 stars that show unexplained infrared excess with no obvious natural explanation. Dr. Matthias Suazo, lead researcher, emphasizes caution. He says, "These could still be natural phenomena we don't fully understand. Unusual dust distributions, protoplanetary disks in unexpected configurations, but they warrant detailed follow-up." Follow-up spectroscopy is ongoing. If any of these candidates are confirmed as having truly anomalous properties that resist natural explanations, they would become the best Dyson Sphere candidates we've ever found. But as of 2025, the jury is still out. The lack of confirmed Dyson spheres isn't just an observational puzzle, it's a profound mystery called the Fermi paradox. Enrico Fermi asked the question in 1950, "Where is everybody?" The galaxy is 13.6 billion years old. It contains 200 to 400 billion stars. Many have planets. Many of those planets are in habitable zones. Even if intelligent life is rare, even if only 1 in a billion stars develops technological civilization, there should be hundreds of civilizations in our galaxy alone. Many would be far older than us. If a civilization reached our current level just 10,000 years before us, a blink of an eye cosmically, they'd be incomprehensibly advanced by now. And Dyson spheres are a logical step in technological development. They provide essentially unlimited energy. They're detectable across the galaxy. So where are they? Dr. Jeffrey Landis proposes the percolation theory. Advanced civilizations exist, but expansion is slower than we expect. They haven't reached our region of the galaxy yet. Dr. Robin Hanson suggests the Great Filter. Something prevents civilizations from reaching the Dyson Sphere stage. Perhaps technological civilizations destroy themselves. Perhaps there's a natural disaster we haven't yet encountered. Or perhaps, as proposed by Dr. Milan Cirkovic, advanced civilizations deliberately remain undetectable. They build Dyson spheres around dim red dwarf stars that are hard to observe. They use technology more efficiently than we imagine, reducing waste heat to undetectable levels. The lack of Dyson spheres could mean many things, but it definitely means something profound about intelligence, technology, and cosmic destiny. But this represents just one piece of a much larger puzzle hidden in the mathematics of stellar engineering. In 1964, Soviet astronomer Nikolai Kardashev proposed a classification scheme for civilizations based on energy consumption. Type 1 civilization can harness all energy available on their home planet. This includes all solar energy hitting the planet, all geothermal energy, all tidal energy, approximately 10 to the 17th watts. Type 2 civilization can harness all energy from their host star, a civilization with a complete Dyson sphere, approximately 10 to the 26th watts. Type 3 civilization can harness all energy from their galaxy, Dyson spheres around billions of stars, approximately 10 to the 37th watts. Humanity currently sits at approximately 0.73 on this scale, not even Type 1 yet. We use mostly fossil fuels with growing renewable energy. We don't capture all available solar energy. We don't control weather or tectonics. Dr. Carl Sagan estimated that if energy consumption continues growing at historical rates, humanity could reach Type 1 in 100 to 200 years, Type 2 in a few thousand years. But here's what's profound. The jump from Type 1 to Type 2 is enormous. It's not just a quantitative change, a billion times more energy, it's a qualitative transformation. A Type 2 civilization wouldn't worry about energy, ever. They could terraform any planet in their system within decades, build continent-sized habitats in space, create artificial gravity through rotation on any scale, power particle accelerators the size of planetary orbits, run simulations complex enough to model entire biospheres in real time, potentially extend individual lifespans indefinitely through perfect medical technology. Dr. Freeman Dyson calculated something remarkable. A civilization with a complete Dyson sphere could sustain more biological activity than the entire Earth supports by many orders of magnitude for longer than the current age of the universe. A single Dyson sphere could host more life, more minds, more art and science and culture than all of Earth's history combined. And if civilizations naturally progress through these stages, the galaxy should be filled with Type 2 civilizations. Each would be blazingly obvious in the infrared. The fact that we don't see them is the Fermi paradox again, restated in thermodynamic terms. One of the most compelling arguments for the inevitability of Dyson spheres comes from self-replicating machines. Dr. Robert Freitas calculated in 1980 how long it would take self-replicating probes to colonize the galaxy. Assumptions. Probes travel at 10% the speed of light, achievable with fusion propulsion. They take 500 years to reach a new star system. They spend 100 years replicating and building new probes. Then they send out more probes. Under these conservative assumptions, the entire galaxy could be explored and colonized in approximately 4 million years. That sounds like a long time, but the galaxy is 13.6 billion years old. 4 million years is 0.03% of galactic history. If any civilization anywhere had started this process more than 4 million years ago, their probes and colonies should be everywhere, including here. Dr. John von Neumann, who first conceptualized self-replicating machines, noted the exponential nature. The first probe is hardest. After that, each generation doubles. Exponential growth inevitably saturates available resources. Applied to Dyson Spheres, the first solar collector is hardest to build, but once you have energy-producing infrastructure in space, building more becomes easier. Use collectors to power mass drivers. Use mass drivers to launch raw materials from Mercury. Use materials to build more collectors. The process accelerates. Dr. K. Eric Drexler, analyzing nanotechnology-enabled construction, estimated that a mature, self-replicating space infrastructure could construct a complete Dyson swarm in less than 30 years. 30 years to go from a few orbiting factories to complete stellar energy capture. If such technology is possible, and physics suggests it is, then any civilization that reaches space should build Dyson spheres quickly. And yet, we see none.
Perhaps there are physical limits we don't yet understand. Dr. Milan Cirkovic proposed what he calls the aestivation hypothesis. Advanced civilizations might deliberately wait. The reasoning is computational. If your civilization's goal is maximizing information processing and conscious experience, you'd notice something interesting about thermodynamics. Computation generates waste heat. In a hot universe, like ours, at 2.7 Kelvin cosmic microwave background temperature, cooling computers is expensive energetically. But the universe is expanding and cooling. In a few trillion years, the cosmic microwave background will be colder. Computation will be more efficient, more calculations per unit of energy. Rational civilizations might therefore enter hibernation, waiting for a colder universe where their energy can be used more efficiently. This would explain why we don't see Dyson spheres. Civilizations build them, accumulate energy, then shut down to wait for better cosmic conditions. It's a speculative idea, but it's based on real physics. Another possibility, proposed by Dr. Robin Hansen, civilizations discover new physics. Maybe there's a way to extract energy directly from vacuum fluctuations, or tap into higher dimensions, or access zero-point energy. If so, Dyson spheres would become obsolete. Why build a megastructure around your star when you can extract unlimited energy from empty space? We haven't discovered such technology, but we've only been doing physics seriously for 400 years. A civilization 10,000 years more advanced might know physics we can't even imagine. If new physics makes Dyson spheres unnecessary, we wouldn't find them. Not because civilizations don't advance, but because they advance beyond the need for them.
There's another explanation for the Great Silence, popularized by Chinese science fiction author Liu Cixin, the dark forest hypothesis. The idea, the universe is filled with civilizations, but they remain hidden because revealing yourself is existentially dangerous. Consider, if you detect another civilization, you face a terrible problem. Are they friendly? Hostile? Indifferent? You can't know. Communication takes years or centuries. By the time you receive a response, they might have changed. They might be building weapons. They might be expanding toward you. The safest strategy, according to game theory, is preemptive elimination. Destroy any civilization you discover before they can threaten you. If all civilizations reason this way, the galaxy becomes a dark forest, filled with hunters staying silent, because making noise attracts predators. In this scenario, Dyson spheres would be suicide. They're too obvious, a glowing infrared beacon announcing, "Advanced civilization here. We have resources you could use." Any civilization building a Dyson sphere would be destroyed by others practicing dark forest strategies. So, civilizations remain hidden. They use their star's energy efficiently enough to survive without a complete sphere. They expand slowly, carefully, staying beneath detection thresholds. Dr. David Brin calls this the Great Silence, not because the universe is empty, but because everyone is hiding. It's a dark explanation, and it has troubling implications for humanity's future. If the dark forest is real, our radio transmissions, our deliberate METI messages to nearby stars, might be catastrophically unwise. We might be children shouting in a forest full of predators. The evidence extends beyond the question of detection into the realm of human destiny itself. Let's talk practically about building a Dyson swarm. First challenge, materials. You need mass, lots of it. Mercury is the obvious choice, close to the sun, no atmosphere, low gravity, rich in metals. Mercury's mass, 3.3 times 10 to the 23rd kilograms. Mass needed for Dyson swarm, about 10 to the 20th to 10 to the 22nd kilograms, depending on collector thickness. Verdict: feasible. Mercury alone provides more than enough. But getting that mass into orbit is non-trivial. Even with Mercury's low gravity, 0.38 g, launching quadrillions of tons requires enormous energy. Solution: mass drivers, electromagnetic catapults that accelerate packages to escape velocity using solar power. Build a few collectors first. Use their energy to power mass drivers. Use mass drivers to launch materials that become more collectors. Exponential growth solves the energy problem. Second challenge: orbital mechanics. Each collector must orbit stably. Too close to others, and they collide. Orbits must be chosen carefully to maximize coverage while minimizing collision risk. Dr. Stuart Armstrong modeled optimal orbits. The solution: place collectors in multiple orbital shells at different radii with different inclinations, carefully timed to avoid intersections. Think of it as a three-dimensional shell game with billions of pieces in motion, their positions calculated by supercomputers to ensure stable configurations. Third challenge: station keeping. Even carefully planned orbits aren't perfect. Gravitational perturbations from planets, radiation pressure, and interactions between collectors cause orbital drift. Each collector needs minor propulsion, ion drives powered by the solar energy they collect, constant, tiny adjustments to maintain proper orbits. Fourth challenge: communication and control. Coordinating billions of independent collectors requires a communication network. Each collector needs sensors to detect neighbors, computers to calculate corrections, and transmitters to report status. But this is actually easier than it sounds. Modern technology already handles networks of billions of devices, the internet. Scale up processing power by a factor of 1,000,000, achievable with sufficient energy, and the problem becomes tractable. How long would it actually take? Dr. Stuart Armstrong's 2013 paper modeled this in detail. Phase 1. Initial infrastructure, years 1 through 50. Launch automated mining facilities to Mercury. Establish orbital construction yards. Build first-generation solar collectors, 1,000 to 10,000 units. Develop self-replicating factory technology. Phase 2. Exponential growth, years 50 to 500. Each collector provides energy for more construction. Mining and manufacturing scale exponentially. Collector count doubles every 2 to 5 years. By year 500, millions of collectors online. Phase 3. Majority coverage, years 500 to 1500. Continued exponential growth. Stars' visible light output begins noticeably declining. Collector numbers in billions. 50 to 70% stellar energy capture achieved. Phase 4. Completion and optimization, years 1500 to 2000. Final collectors added to fill gaps. Orbit optimization to maximize efficiency. 95% plus stellar energy capture. Transition to maintenance mode. Total time? Approximately 2,000 years. On cosmic timescales, this is instantaneous. On human timescales, it's 60 to 80 generations. A child born when construction begins would not live to see completion, but their great-great-great-grandchildren would inhabit a civilization transformed. So you've built your Dyson swarm. You now command 10 to the 26th watts. What do you do with it? Option 1, maximize population. Build O'Neill cylinders, massive rotating habitats providing artificial gravity through spin. Each cylinder could house millions of people in Earth-like conditions. With a complete Dyson Spheres energy, you could build millions of O'Neill cylinders. Total population capacity, 10 to the 15th to 10 to the 18th individuals. That's 1 million to 1 billion times Earth's current population, all living at high standards, sustained indefinitely. Option 2, maximize computation. Maybe consciousness uploads become possible. Maybe minds can exist as software in vast computer networks. Dr. Seth Lloyd from MIT calculated the maximum computational capacity of matter, using Dyson Sphere energy to power computers built from all available mass in a solar system. You could run approximately 10 to the 51st operations per second. That's enough to simulate billions of Earth-like worlds in perfect detail, updated in real time, running thousands of times faster than actual time. Every human who ever lived could be simulated. Every possible human could be simulated. Entire civilizations, histories, universes, all running simultaneously. Option 3, maximize expansion. Use the energy to build starships, fusion-powered, capable of 10 to 20% light speed, carrying self-replicating probes to nearby stars. With a Dyson Spheres energy, you could launch thousands of colony ships per year. Within 1 million years, your civilization could span the galaxy. Option 4, scientific research. Build particle accelerators the size of planetary orbits. Create conditions not seen since microseconds after the Big Bang. Test theories of quantum gravity. Search for new physics. Build telescopes with apertures measured in astronomical units. resolve exoplanet surfaces light years away, map the universe in unprecedented detail. This forces us to reconsider fundamental assumptions about the purpose and trajectory of technological civilization. Current and planned missions will dramatically improve our ability to detect Dyson spheres. James Webb Space Telescope, operational now, extraordinary infrared sensitivity, can detect waste heat from partial Dyson swarms thousands of light years away, already analyzing anomalous infrared sources. Extremely Large Telescope, 2028, 39-meter mirror, will directly image exoplanets, could potentially detect megastructure shadows. Habitable Worlds Observatory, 2040s, designed to characterize Earth-like planets. Infrared capabilities for detecting waste heat will survey thousands of nearby stars. Breakthrough Listen, ongoing, radio and optical SETI program, searching 1 million nearby stars, looking for both intentional signals and technosignatures like Dyson Spheres. Dr. Jill Tarter, former director of SETI research, notes, "We've searched perhaps 0.000000001% of the parameter space for extraterrestrial intelligence. It's like dipping a glass into the ocean and concluding there are no fish because you didn't catch one." The next 20 years will dramatically expand that search. If Dyson spheres exist within a few thousand light years, we have a reasonable chance of finding them. The discovery of a confirmed Dyson sphere would be the most important event in human history. It would prove definitively that 1. We are not alone. Intelligent life exists beyond Earth. 2. Advanced civilizations can survive. Whatever great filter might exist, at least one civilization passed it. 3. Stellar engineering is possible. The physics and engineering we think should work actually does work. 4. Long-term thinking is achievable. A civilization maintained focus and stability long enough to complete a multi-generational mega-project. But it would also raise terrifying questions. Why only one? If building Dyson spheres is inevitable, why aren't there millions? What prevents most civilizations from reaching that stage? Should we contact them? A civilization capable of stellar engineering might see us as resources, raw materials, or worse, computational substrate. Revealing ourselves could be catastrophic. Are we behind schedule? If other civilizations reached this level millions of years ago, why are we only now developing technology? Are we unusually slow? Unusually lucky? Dr. Seth Shostak from SETI notes, "The confirmation of extraterrestrial intelligence would immediately make every human problem seem smaller, but it would also make the question of our cosmic future infinitely more urgent." Let's make this personal. Could humanity, specifically, build a Dyson sphere? Current assessment, not yet, but soon. What we'd need: technology, advanced robotics and AI, self-replicating manufacturing, space mining and refining, orbital construction capabilities, efficient solar panel production. Where we are? Robotics, advanced and improving rapidly. AI, capable of complex tasks, improving exponentially. Space mining, demonstrated in concept, not yet industrial scale. Orbital construction. ISS proves concept, need massive scale-up. Solar panels, mature technology, need adaptation for space. Timeframe estimate. Assuming continued technological progress, 2100 self-replicating factories on Earth, 2150 first automated mining operations on the Moon, 2200 industrial-scale space manufacturing, 2250 first Mercury mining operations, 2300 first Dyson swarm collectors deployed, 2500 to 4500 exponential growth to completion. That's 300 years until we start, 500 to 2,000 years to finish. Long on human timescales, instantaneous on cosmic timescales. Dr. K. Eric Drexler, nanotechnology pioneer, believes it could happen faster. Once molecular nanotechnology matures, perhaps by 2050, the constraints change completely. Self-replicating assemblers could build Dyson collectors atom by atom. The timeline collapses to decades. But there's a catch. We have to survive long enough. Climate change, nuclear weapons, bioengineered pandemics, AI misalignment, asteroid impacts. All pose existential risks in the next century. If we navigate these dangers, if we mature as a civilization, Dyson spheres aren't just possible, they're probable. Recent breakthroughs in fusion energy, ITER approaching break-even, advanced materials, graphene, carbon nanotubes, and space launch costs, such as SpaceX reducing prices 100-fold, suggest we're on track. The infrastructure is coming together, the knowledge is accumulating, the vision is crystallizing. Humanity might build a Dyson sphere. Not us, not our children, but our descendants 1,000 years hence might look back at our era as the moment when the dream began.
Building a Dyson sphere raises profound ethical questions. Question 1. Do we have the right? The sun belongs to Earth's biosphere. Its light enabled photosynthesis, which created our oxygen atmosphere, which enabled complex life. Every living thing on Earth exists because of the sun. Do we, one species living in one moment of cosmic time, have the right to fundamentally alter the sun's relationship with its planets? If we build a Dyson swarm, Earth's sunlight dims, plants die, the biosphere collapses. We'd need to move the biosphere to orbital habitats or terraform Mars and Venus, or accept extinction of every species except those we deliberately save. Dr. Christopher McKay, planetary scientist, argues the biosphere has rights, not legal rights, we create those, but moral rights grounded in the intrinsic value of life. Any Dyson Sphere project must preserve Earth's biosphere completely and indefinitely. Question 2. What about other planets? Venus, despite being hellish, might harbor life in its upper atmosphere. Mars might have subsurface microbes. Europa and Enceladus have subsurface oceans. Building a Dyson swarm affects all these worlds. Less sunlight means colder surfaces, different chemistry, changed evolutionary pressures. Do potential microbes on other worlds have a say in our stellar engineering project? Question 3. Future generations.
A Dyson sphere is irreversible. Once built, dismantling it would be catastrophic. The civilization depending on it would collapse instantly without its energy. Are we justified in making permanent decisions that bind our descendants forever? Or is this exactly what technological progress always does? Agriculture was irreversible, civilization was irreversible, industrialization was irreversible. Perhaps Dyson spheres are just the next step in an inevitable trajectory.
Here's where it gets strange. Philosopher Nick Bostrom proposed the simulation argument in 2003. It states that one of three things must be true. 1. Civilizations almost never reach the technological level to run ancestor simulations. 2. Advanced civilizations choose not to run ancestor simulations. Or 3. We are almost certainly living in a simulation. The reasoning? If Dyson spheres are possible, and if they provide enough computational power to run detailed simulations of entire civilizations, then a single Type 2 civilization could run millions or billions of simulated realities. Each simulation could contain billions of conscious beings who believe they're in a real universe, not knowing their software running in computers powered by a Dyson sphere built by a civilization that existed billions of years ago. If this is possible, then the number of simulated beings vastly exceeds the number of real beings. Statistically, you're more likely to be simulated than real. The simulation argument connects directly to Dyson spheres. They provide the computational infrastructure to make simulations feasible. Dr. David Chalmers, philosopher of mind, notes, if Dyson spheres are built, and if consciousness can be substrate independent, then most conscious beings in the universe are probably simulated. This has profound implications for the nature of reality. Are we real, or are we simulations running in computers powered by a Dyson sphere built by a civilization that existed billions of years ago? There's no way to know, but the possibility emerges directly from the physics of stellar engineering. The most profound implications emerge when we consider the ultimate fate of the universe. Current cosmology suggests the universe will expand forever, gradually cooling. Stars will burn out, galaxies will drift apart. Eventually, only black holes remain, then even those evaporate. This is called heat death, the slow, cold, dark ending of everything. But Dyson spheres change the equation. Dr. Freeman Dyson, in his 1979 paper, Time Without End, showed that an intelligent civilization with sufficient energy could survive indefinitely, even in a dying universe. The strategy? 1. Build Dyson spheres around long-lived red dwarf stars. 2. As those stars die, harvest energy from black holes via Hawking radiation. 3. Slow down your civilization's metabolism. Think slower, live in slower time. 4. By thinking slower, you use less energy per thought. 5. Stretch your civilization's lifetime indefinitely. He concluded,
A sufficiently advanced civilization could experience an infinite number of thoughts using only finite energy. Infinite subjective experience in a finite universe. Immortality through time dilation and energy conservation. But it requires stellar engineering. It requires Dyson Spheres or their equivalents, and it suggests something profound. Intelligence isn't a brief flash in the cosmic dark, it's potentially eternal. Advanced civilizations don't go extinct, they slow down, adapt, and persist, outliving stars, galaxies, even the universe's ability to form new structures. The universe might be ancient not just in time, but in accumulated experience. Civilizations billions of years old, thinking slowly, surviving on the dregs of energy leaked from evaporating black holes, waiting in the cold dark for the heat death to complete. And we might be infants in comparison. Our entire history, from the first stone tools to space telescopes, might be a microsecond in the subjective time of such beings. Dyson spheres are the beginning of this trajectory, the first step toward cosmic immortality, the transition from beings who merely exist in the universe to beings who shape it, survive its ending, and persist beyond. We began with a structure that completely surrounds a star. Now we understand what that represents. A Dyson sphere isn't just an engineering project. It's a statement, a declaration that a civilization has matured beyond planetary limitations, beyond dependence on a fraction of their star's energy, beyond the boundaries of their birth world. It's the visible signature of a Type II civilization, the most detectable sign of intelligence we could hope to find. And yet, we haven't found one, not definitively. The Fermi paradox remains, the great silence persists, but the search continues. Project Hephaistos analyzes millions of stars. JWST peers into infrared wavelengths. Future telescopes will survey billions of stars across the galaxy. If Dyson spheres exist, we will find them, and when we do, humanity will face its most important decision: remain silent observers or reveal ourselves to a universe that might be far more crowded and far more dangerous than we imagine. For ourselves, the question is simpler: will we build one? The physics says yes, the engineering says yes, the economics, unlimited energy, unlimited living space, unlimited potential say yes. But we have to survive first, navigate the next century without destroying ourselves, mature from a fractious planetary civilization into a unified species capable of long-term thinking. If we do, if we succeed where countless others might have failed, then our descendants will build it. They'll start with Mercury, mine its metals, launch materials into solar orbit, deploy the first collectors. And slowly, over centuries, the sky will change. The sun will dim, not because it's dying, but because its energy is being captured, used, transformed into the infrastructure of a mature civilization. Earth might be transformed into a garden world, a nature preserve, a memorial to our origins. Or it might be dismantled, its atoms incorporated into orbital habitats housing trillions. Either way, our species will have crossed a threshold, from being children of the sun to being engineers of stars. And somewhere in the darkness between stars, we might be the first, or we might be the last, or we might be one of many, our signals not yet reaching each other across the cosmic distances. But the imperative is clear. If we want to survive, if we want our civilization to persist for more than a few thousand years, We must think bigger, not just in terms of technology, but in terms of vision, purpose, destiny. Dyson spheres aren't merely possible. For any civilization serious about the future, they're necessary. The question isn't whether to build them. The question is whether we'll survive long enough to try.